So today we're going to start chapter 5 about integration. This is really, really important. We've got about 4 class periods to talk about integration. We want to start simple and build up to more complicated things. And the simplest way I can think of to start here is thinking about motion again. We will come back to parametric equations, but not right now. Keep it simple. Imagine you've got a bug walking along a straight line across a page, which sounds like parametric equations, right? We did the other day, but focus just on how far the bug has traveled. Say the bug travels along a line here, starting right there and traveling to the right at a constant speed. Keep it simple. What constant speed? Let's pretend the bug walks at 2 centimeters per second. Say about this fast across the page, starts at that point at t equals 0, and ends at this point at t equals how long? Let's say 5 seconds have gone by. Question is, how far is the bug gone? I hope it's pretty clear that you just multiply the rate, 2 centimeters per second, times the time. Distance equals rate times time. You know, that's something you learned about in physics, maybe even earlier, maybe 7th or 8th grade. You learned that distance equals rate times time when the motion is at a constant rate, when the speed is constant. So the bug's moving at a uniform rate, a uniform speed. It's like you're in your car and you set the cruise control, right? You're going at a constant speed. So the rate here is 2 centimeters per second, and the time is 5 seconds. The seconds do cancel, giving you an answer of 10 centimeters. The bug has traveled 10 centimeters in those 5 seconds if it travels at a constant rate of 2 centimeters per second. That's the simplest kind of example about integration. Wait, did we do an integral there? We really did. Where? I don't see an integral symbol. Well, you have to set it up mathematically. What did we really do? We knew the bug's speed as a function of time is a constant function 2. Going to make a graph. Axes are going to be labeled t and v. V in general for velocity, but keep in mind that if the velocity is always positive, it's the same as the speed. In general, the speed is the absolute value of the velocity. The velocity can be negative if the bug travels back and forth, sometimes in the positive direction, sometimes in the negative direction. Or if you've got a ball going up and down, sometimes it's going up in the positive direction, sometimes it's going down in the negative direction. Velocity can be positive or negative. The speed, what your speedometer says, is the absolute value of the velocity. And in general, if you're talking vectors, which we will come back to, the speed is the length of the velocity vector. But here, our velocity function, our speed function is constant. It's a horizontal line at 2 centimeters per second. V is in centimeters per second. T is in seconds. The bug traveled for 5 seconds. So this graph is valid from t equals 0 to t equals 5. And when we did this product to find the distance traveled, geometrically, that's the same as finding the area under this graph. It's the area of this rectangle. Its height is 2. Its base or width is 5. Units would be 2 centimeters per second for the height. I know that's kind of a strange unit to call it a height. It's not a literal distance. It's the units for the variable itself, but in the picture, it's a height. And the horizontal, the width, or the base, is 5 seconds. Again, that would be a strange unit for a literal distance. Just keep in mind it's the units for the horizontal axis variable. And so when you multiply, it does give you geometrically the area under this curve, which is an area of a rectangle. The area equals 2 centimeters per second times 5 seconds. It equals 2 centimeters. Okay, again, usually units of area are square centimeters. Just don't worry about it. You're taking the units for the horizontal axis, whatever they are, and the vertical axis, and multiplying. Centimeters per second times seconds is centimeters. It's not that I've literally drawn a rectangle that has 2 square centimeter area or something like that. It's a way of visualizing what's going on here. And that area is represented by a definite integral symbol. You make an integral sign like we've done with indefinite integrals. You put the function that's being integrated right here. In this case, it's the constant function 2. That's the function that I'm finding the area under the curve for. And that's what definite integrals are all about, is finding areas under curves. The constant function, that horizontal line there. You should emphasize the variable is t, so you put a dt here. And there's a good reason to put a dt instead of just a t there. I will get into that as we keep going here. But you don't leave it like that. You put limits of integration. If this were all I was going to write, if I was just going to write an indefinite integral, you'd say, oh, I guess that's an antiderivative, 2t plus c. But I don't want an antiderivative here. I want the actual distance traveled. So I write this as a definite integral. I put limits of integration, the lowest value of t, 0, and the highest value of t, 5. Those are called limits of integration. It's perhaps unfortunate to use the word limits there, because they're not limits in the usual sense of calculus. Those are limits of integration. I'm not taking a limit. They're just the endpoints of the interval that I'm thinking about here from 0 to 5. The function being integrated is called the integrand. And the dt, what is that? Well, it's just telling you the variable, the independent variable is t. Technically, dt is called a differential. There's one word for it. Another word for it is an infinitesimal. I'm not going to explain what that means right now. That's the function I'm finding the area under the curve for. And because the graph is a horizontal line, that area is just the area of a rectangle, base times height. Nothing much to do there. But already here in this first day on integration, beginning of chapter 5, I'm going to talk about, near the end of chapter 5, I'm going to talk about the fundamental theorem of calculus. Right now, sounds important, fundamental theorem of calculus. Right now, this is Newton and Leibniz's greatest discovery in math, is realizing this is true, that you can find the area by essentially doing an indefinite integral, finding an antiderivative, plugging in the top limit of integration, and subtracting what you get when you plug in the bottom limit of integration. What's an antiderivative of this? Well, it's 2t plus c. Well, guess what? You don't need to put the plus c, because when you do the subtraction that I mentioned 30 seconds ago, the c would end up canceling anyway. You put the limits of integration over here, and what this means is it means plug in the top number and subtract what you get when you plug in the bottom number. That's standard notation. 10 minus 0 is 10. Oh, yeah, the answer is 10. Well, I already knew that. Because the area is the area of a rectangle. But that's a simple example because it's a rectangle. What if it's a more complicated speed function? And the area is not the area of a rectangle or maybe the area of a triangle. It's something more complicated. How do you find the area? Newton and Leibniz realized you can still use an antiderivative. People were finding areas and slopes before Newton and Leibniz came along. Even 2,000 years ago, Archimedes was thinking about areas of circles, for example, right? That's how pi came about. They didn't have our decimal system back then, so I don't know exactly how they thought about pi. They didn't say it was 3.14159, blah, blah, blah. They didn't have decimals. So I don't know exactly how they thought about it, except geometrically. I didn't know how they estimated it, though they knew it was close to 3 in the usual sense of 1, 2, 3. And people were figuring out slopes of tangents before Newton and Leibniz came along. A person named Fermat was thinking about slopes of tangents. But it's the tying together of the two. The fact that I can use an antiderivative to find an area, that was the big realization. And again, not just in simple examples like this, but in any example where the speed is some nice continuous function, at least. Can I clarify anything? This is the simplest kind of example. And yeah, what I used here is, it's called the fundamental theorem of calculus. You could write it all out. I'm just going to write FTC for short. Fundamental theorem of calculus, illustrating that I used an antiderivative 2t. What is an antiderivative? Its derivative is 2, the integrand function. I'm using that antiderivative and plugging in the limits of integration to find the area. The next step up in difficulty is, well, we're once again going to think about a bug traveling along a line here. It's there at t equals 0, and it's here when t equals 5 again. And it's traveling to the right, just like before, but now I'm going to make it a little trickier. Instead of a constant speed, it's going to have a constant acceleration. That's harder. Acceleration is harder to imagine, right? Constant speed's a little easier to imagine because you just are in your car and you just set the cruise control, right? That's kind of easy to imagine. How do you imagine a constant acceleration? Well, I mean, we talk about how when you drop an object, the force of gravity is essentially constant, and that makes it a constant acceleration. But that does mean it's speeding up. It's going faster as it falls downward. And how do you really conceptualize that, other than to say that every second that goes by, it's going 9.8 meters per second faster? I mean, you can say that, but how do you say exactly what that means besides those words? You use math, you use functions. Now the velocity is going to be a function of t. I'll write v equals f of t. Sometimes people abuse notation here and write v equals v of t using the same letter v to represent both a dependent variable and a function name. It's a common thing people do, but it's technically not good. It's called abuse of notation. Not abusive notation, but abuse of notation. If it's done, don't worry about it. It's not a big deal. I'll try to use function notation. F is the name of the function. What is this function? Well, it could be lots of different things. If I try to make the distance traveled still 10 like before, the average speed better be 2 centimeters per second. Let's see, how do I make the average speed 2 centimeters per second over 5 seconds? A little tricky. I think I need it to be, what, maybe 2/5 t? That'd be right. Or 4/5 t, maybe. I think it's 4/5 t. Gotta think about that for a second. Yeah, that'll work. I'm purposely picking an example that's still going to make the total distance traveled 10 centimeters. I could have done something different. If that's the speed, in centimeters per second. Notice it's a function of t. It's a linear function of t. It's not any old function of t. Its graph is a straight line, though it's got a positive slope, not a zero slope. The average speed is going to be the average of its values at t equals 0 and t equals 5. Its value at 0 is 0. Its value at 5 is 4 centimeters per second. The average of 0 and 4 is 2. I can't really use the distance equals rate times time equation anymore unless I think of the rate as the average speed, which again, I could do, and it would be still 2 centimeters per second, and it's still going to get the same answer. Well, let's pretend we don't know that. What's the graph of the velocity look like? And again, it'll be a positive velocity, so that's the same as the speed. Velocity is in centimeters per second. Time is in seconds. I'm letting time go from 0 to 5. The velocity goes up in a linear way. The fact that that graph is a straight line means its derivative is constant, but the derivative of the velocity is acceleration. The acceleration is, the derivative of that is 4/5 centimeters per second squared. 0.8 centimeters per second squared. That would be a constant acceleration. The bug is speeding up, though. It starts out slow and goes faster and faster as it walks. By the end, it's up to 4/5 times 5 is 4 centimeters per second. It's still the area under the graph that gives you the distance traveled. I haven't fully justified that, but that is correct. Well, what is that area? That's the area of a triangle. 1/2 base times height. 1/2 times base is 5 seconds. Times height is 4 centimeters per second. The seconds once again cancel. 1/2 times 5 times 4 is 10 centimeters. Same final answer. 10 centimeters. Same distance traveled. And yes, that is the same as the average of the two extreme speeds, 0 centimeters per second and 4. The average of 0 and 4 is 2. On average, the bug is traveling 2 centimeters per second over 5 seconds. That's why the bug goes 10 centimeters. But you can only do that average because this function's linear. If it were a function that's nonlinear, like t squared or something really weird going up and down, the bug goes faster than slower, then faster than slower, then faster than slower. It's not obvious that the average speed would be halfway between the extremes, and it's probably not right either. Am I making sense here? You can think intuitively about these things, not looking completely for rigorous proof. This distance traveled, this area can also be written as an integral. Integral from 0 to 5 of this speed function, 4/5 t. When I'm thinking about these areas and I'm thinking about speeds and distance traveled and integral symbols, I'm really doing 2 sections of chapter 5 at once here. First section and second section. First section is just about the physics of it and the idea of the area giving you the answer. The second section is about the integral symbol. And actually, by using the fundamental theorem of calculus, I'm talking about the third section of chapter 5. So I'm kind of mixing 3 sections of chapter 5 together here. I think pedagogically speaking, and that's a good idea. But as far as your homework goes, you will not have to be writing these integral symbols for the homework due next Monday. Well, I probably will give a few problems from 5.2, so you may have to do a couple problems like that. But most of the problems will be from 5.1. I think I will do a little bit from 5.2. But you will not be using the fundamental theorem of calculus for the homework due Monday. not until next Wednesday. But what does it say? It says to evaluate the integral, do an indefinite integral. Find an antiderivative of what? 4/5 t, this integrand function. How? Guess. Seriously. I guess it's got to involve a t squared, right? Something times t squared. T squared is not the final answer, though, because its derivative is 2t, not 4/5 t. A little bit of guesswork helps you realize it's 2/5 t squared, right? Think about taking the derivative of that. The derivative of 2/5 t squared is 4/5 t. That's an antiderivative. Do I need a plus c? No, because when I do the subtraction, the c would cancel anyway. When you do definite integrals, you don't need the plus c. So why do we emphasize plus c with indefinite integrals? It's because it's helpful for differential equations mostly. Which we will talk about a little bit here before exam 3. Again, the vertical line here means evaluate this from 0 to 5, which means plug in 5 into this antiderivative and then subtract what you get when you plug in 0. So we get 2/5 times 5 squared minus 2/5 times 0 squared. 2/5 times 25 minus 0 is 25, and the 5 cancel to give you 2 times 5 is 10. 10 centimeters, same answer. Okay. Can I clarify anything there? This is super important stuff. The other thing important about all this is it applies beyond physics. We'll talk about this more next week, but anytime you have an integrand function that represents the rate of change of something, as a speed does, the integral gives you the total change. So we're integrating the speed, we're getting the total change in position, you might say, the distance traveled. It's not quite the same as change in position unless you're just moving in one direction. This is effectively ending position minus starting position, going in one direction. So this is the distance traveled. But again, this generalizes. Next example. Bug starts here at t equals 0, ends here at t equals 5. Moving to the right, but let's say now the velocity or speed is a quadratic function. I got to think carefully about how to make it so that the distance traveled still ends up being 10. Okay, I'm doing that just for fun. I could pick something different. Let's see, how can I do it so the distance traveled ends up still being 10? Thinking in my head here. Over 5 seconds still. It's a little tricky to do. Okay, let me not be artificial like that. Okay, let's just pick something simple, t squared. Can't do that calculation in my head on the spot. I know it involves 125 over 3, but I'm not going to go into other details. I was getting confused about fractions in my head. Don't worry about that. So that's now the new speed, t squared. Not constant speed, not linear speed, quadratic speed. V is still in centimeters per second, t is still in seconds. The graph, which, well, I'm drawing in such a way that it's not to scale. These scales on the axes are different. Looks like this, and when t is 5, the velocity is 5 squared is 25 centimeters per second. the distance traveled is still the area under the curve. I will try to justify that, but hang on, let's just figure it out. This area is still the distance traveled. But it's no longer a rectangle, it's no longer a triangle. It's a curvy triangle, maybe you might say. I guess the area would have to be less than the area of a triangle I could draw in here like that, whose area 1/2 base times height would be 1/2 times 5 times 25. 5 times 25 is 125 divided by 2 is 62.5. The area's got to be less than 62.5. Distance travel's got to be less than 62.5 centimeters. Some number less than that. What is it exactly? That's for the fundamental theorem of calculus. Symbolically, I can still write the distance traveled as an integral, a definite integral of the speed function t squared with respect to t. T still goes from 0 to 5. Effectively, this equality here is section 5.1. This equality here is section 5.2 in the book. That's what I'm talking about here. And the next equality is section 5.3. It's the fundamental theorem of calculus. Find an antiderivative of t squared. Plug in 5, subtract what you get when you plug in 0. What's an antiderivative of t squared? It's got to involve a t cubed. You did okay on this on the last exam. The answer is going to be 1/3 t cubed. You evaluate from 0 to 5 means you get 1/3 times 5 to the 5th minus 1/3 times 0 to the 5th. Oops, 5, what am I doing? 5 to the 3rd. 5 to the 3rd is 125. 0 to the 3rd, 0. 125 over 3. What is that? 41.6 repeating, I guess? Centimeters. That's how far the bug traveled. Of course, you don't want infinitely many significant digits in a real life problem. You don't want to round that. 41.7 centimeters, maybe. Of course, another issue is why would a bug travel like without exactly that speed? T squared, right? No bug would do that. With real life data, real life's more complicated than simple functions like this. However, we can often use simple functions like this to approximate real life data. That's often done, giving us an approximate answer. If this were the exact real life function somehow to infinitely many digits of precision, then this would be the exact distance traveled to infinitely many digits of precision. But that would never happen in real life, right? And you can't measure to that precision if nothing else. In math, we do idealized examples. And then when we apply the math, we are essentially doing approximations. But why is the area of the distance traveled? That's perhaps the biggest mystery. Well, not the biggest mystery. The fundamental theorem of calculus is perhaps a bigger mystery. For today, the biggest mystery is why is the area of the distance traveled? This equality there is just a definition. It's just the definition of the symbol. The definite integral is that area. Nothing much to do there. It's just a convenient symbol. You might say it's a weird symbol, but there is a good reason for it. Leibniz was the one who created that, by the way, not Newton. Integral symbol. And he had a good reason for choosing the symbol, which we'll get into for sure next Monday, maybe a little today, we'll see. So how do you justify that as as being correct here today? Well, think of it in terms of approximating the area using simpler regions like rectangles. I'm about to set up some notation and some terminology that's really important if you really want to get this stuff. But people have a little hard time getting used to this. What I'm about to set up are what are called the Riemann sums. Riemann sums. Don't say Riemann, that would really hurt my ears. Riemann was German. When you have an IE in German, it's an E sound. Riemann sums. What's a Riemann sum? Let's talk about it in general. You're given a continuous function. I'm going to go ahead and use the variable x. I could use t for time. But typically people think of this as a function of x when they talk about it. I think the book uses t. Don't let it bother you. It doesn't matter what letter we use. Continuous function f of x over some closed interval from some number a to some number b. This is a closed interval. I'm implicitly assuming a is less than b here. There are two numbers where a is less than b. My goal is to approximate the area under the curve. So I'm really only talking about areas at the moment. Under the graph of f. I'm going to assume f of x is never negative here. Say f of x is always greater than or equal to 0. In trying to approximate this area, I'm still not quite justifying why it would also give you the distance traveled if f of t were the speed. I will come back to that. Approximate the area under the graph of f from x equals a to x equals b. So here's a picture of what's going on. Here's a, here's b. I made them both positive. I didn't have to. Here's the graph of f, nice continuous graph. That's f of x. My goal is to approximate this area with what's called a Riemann sum. What I'm going to do is I'm going to, excuse me, big picture is I'm going to use rectangles and their areas to approximate the area under this curve. That's the big picture of what's going on. You choose a number n, that's the number of subintervals of the bigger interval from a to b, which is going to be the number, same as the number of approximating rectangles. You define, based on that, the width of each rectangle, call it delta x. All these rectangles are going to have the same width. It's the length of the entire interval divided by the number of rectangles, right? If a is 1 and b is 21, the length of that interval is 20, and you want 100 rectangles, they're all going to have width 20 divided by 100, 0.2. B minus a is the length of the interval, and n is the number of rectangles. Do a division. Delta x is b minus a over n. You also define some numbers called x sub I. These numbers have different names. Some people call them partition points. The word partition means you're breaking up the interval into a bunch of pieces, you're partitioning it. You could also think of them as just endpoints of the subintervals. The formula for x sub I is a plus I times delta x. You use this formula for I equals 0, 1, 2, 3 through the number n. What's going on here? X sub 0 is a plus 0 times delta x. That's just a. X sub 1 is a plus 1 times delta x. Well, that's a plus delta x. X sub 2 is a plus 2 times delta x. That's a plus 2 delta x, or I mean times there, etc. X sub n, the last value of I, is a plus n times delta x. That can actually be simplified because you can replace the delta x with b minus a over n and then cancel the n's to leave you with a plus b minus a and then cancel the a's to leave you with b. X sub n is the right endpoint b. In the picture, a is x sub 0. If delta x is this distance right there, if that's delta x, then this is x1. That's a little delta x there if you can't quite see it in the back. If I go another delta x units to the right, then I'm at x2. This distance is also delta x. I go another delta x units to the right, I get to x3. And another delta x units to the right, I get to x4, etc. However many you need to get to b. What do we do with these things? We use them, so what you might call sample points, to plug into the function f to determine heights of approximating rectangles. For example, for each one of these subintervals, the first subinterval, the second one, etc., I could use the left endpoint to determine the height of an approximating rectangle. Go back up to this picture here, look at the first subinterval here of the bigger interval. Its left endpoint is a, which is x0. If I use that value to go up to the function and use the second coordinate of that point as the height of an approximating rectangle over the first interval, that would be my first rectangle, whose area I can easily find as an approximation to the area under the graph over the first subinterval. Then I do it for the second subinterval, that goes from x1 to x2. Its left endpoint is x1. Use that to go up to the function and determine the height of an approximating rectangle. It would look about like this. Go to the next one, x2 to x3. Use the left endpoint to determine the height. It would look about like this, etc. I could use all left endpoints if I wanted to determine heights of approximating rectangles. But why just left endpoints? Why not right endpoints? Well, you could do it with right endpoints too. You would get different rectangles, but they would still approximate the area under the curve. A left-hand Riemann sum is the sum of the areas of rectangles that are made using the left endpoint of each interval. And a right-hand Riemann sum is a sum of areas of rectangles that are formed using the right endpoint of each interval. I'll call them left-hand sum LHS and right-hand sum RHS for short. Think about it symbolically. What's the area of the first rectangle for a left-hand sum? Base times height. The height is f of x0, right? x0 is the left endpoint of the first interval. Plug it into f to find the height. F of x0 is the height. Its base is delta x. For the second subinterval, its left endpoint is x1. Plug that into f to figure out the height. The base is still delta x. It's the same base. Etc. What's the last rectangle? B is xn. The next to last partition point is x sub n minus 1, and that is the left endpoint of the last subinterval here. For a left-hand sum, it is, you plug it into f to find the height. And for a right-hand sum, you use the right endpoints instead of the left endpoints. For the first subinterval, use x1. For the second one, use x2. Plug those into f to find the heights. Multiply times delta x to find the areas. So a right-hand sum looks like this. It's almost the same sum. It is different, but it's almost the same. Many of the terms are the same. The terms that are the same are the ones where the subscript goes from 1 to n minus 1. Those are the terms that are the same. That would include the second to last in this one. The terms that are different are the first one for LHS and the last one for RHS. LHS means left-hand sum, RHS means right-hand sum. You encountered sigma notation before? Summation notation? We're about to use it. People always get kind of scared by sigma notation, including myself when I was younger. We can write these summations using capital sigma notation for summation. I'm talking about the whole sum here. For the left-hand sum, you write capital sigma f of x sub I times delta x. The capital sigma means add terms that look like this. The lowest value of I is I equals 0. You put that down here. That's an I equals 0. That's an I there if you can't quite tell. The highest value of I is n minus 1. Put that up there. That's meant to be a little lowercase I right there. It's just hard to see the dot because it got mixed together with the line. That's meant to be a little I right there. Add up, sigma means add up. It's fortunate that sigma starts with S, sum sigma. That's the reason we use a sigma. Terms that look like this, products that look like this, f of xi times delta x. I starts at 0 and goes up to n minus 1. You assume when you use this notation that I keeps increasing by 1. First it's 0, then it's 1, then it's 2, then it's 3, etc. through the last one is n minus 1. With this one, the summation notation for the whole thing is the same, except I starts at 1 instead of 0 and goes up to n instead of n minus 1. Summation, I goes from 1 to n, not 0 to n minus 1, of f of xi times delta x. Capital sigma means, almost always in math, summation. Question?
What is on top of the summation?
This one's n minus 1, this one's an n. That's an n there. Again, it's assumed when you write this that I keeps increasing by 1 in the summation. First you do f of x1, then 2, then 3, up through the last one's got f of xn in it. I in the summation is really kind of like a variable. First it's 1, then it's 2, then it's 3, then it's 4, etc. when you write this. Over here, first it's 0, then it's 1, then it's 2, then it's 3, etc. I is kind of like the variable. I is an arbitrary index For this formula, it's 0 through n. But in these formulas, this one starts at 0 and goes to n minus 1. Here it starts at 1 and goes to n. It's always kind of scared me. It scares many people when they see summation notation. They can't wrap their minds around it. It's just something to work at getting used to. I mean, I hope it's intuitive that this is going to give you probably a pretty good approximation to the area, at least if n is large. In fact, the larger n gets, the skinnier these rectangles get, the better they approximate the area under the curve. Because over each skinny rectangle, your continuous function doesn't change much. It's almost constant over some small subinterval. It's over larger intervals that continuous functions can change a lot. I mean, if you've got a wildly oscillating function, you could still make your intervals tiny enough that over each interval, they don't change, the function doesn't change much. And the area of the rectangle gives you a really good approximation to the area under the curve. Why does it give you the distance traveled if the function represents speed? If x is t instead? Because it's like in each one of these, you're doing a rate times time. That was the previous page. Distance equals rate times time when the rate is constant. Effectively, over small intervals, even though the speed is changing a little bit, if the time interval is small enough, it doesn't change much, right? Even when you're in your car, when you're hitting the gas, you're accelerating over tiny intervals of time, like 100th of a second, your speed doesn't change very much, even if you're accelerating pretty rapidly. So these are effectively a bunch of distance times rates times distances that are being added together to give a total distance. It is technically an approximation to the total distance, not the exact value. It's the integral that gives the exact value in the fundamental theorem of calculus. Which brings up another question, though, or it should bring up another question. How do you connect these summations to integrals in the fundamental theorem of calculus? What's the connection? It's a limit. Not a limit of integration, but a true limit. Limit as something happens as x goes to 0, or it's a limit as n goes to infinity, or equivalently, delta x goes to 0. As you have more and more rectangles that are skinnier and skinnier, giving you a better approximation to the area under the curve, the definite integral is the limit of such Riemann sums. You can write that the integral from a to b of f of x dx as a limit. Now, this limit equation that I'm writing down is technically not the true definition of the integral. The definition of an integral is more complicated than this is making it seem. But what I'm writing down is really more of a theorem to prove. But effectively, we could think of it as a definition in the sense that it should make sense. It doesn't equal a Riemann sum. It's a limit of Riemann sums. It can be written a limit as n goes to infinity of a Riemann sum like this. Should I use a left-hand Riemann sum or a right-hand Riemann sum? The answer is it doesn't matter, either one. Hey, wait a minute. Where's the n in here? Well, the n is in the delta x. Delta x is b minus a over n. That's where the n is. Let's use Mathematica to check that this is, oops, and that's not, sorry, it's not an infinity up there, it's an n. Let's use Mathematica to check that this is working for our t squared example. So f of t is t squared. We already know the answer for the distance traveled from time 0 to time 5. It was 125 over 3, 41.6 repeating. If you use Mathematica's definite integral symbol over here on the palette, again, you can get to the palettes by going to the palettes menu. One of these three: Basic Math Assistant, Classroom Assistant, or Writing one. I think I usually use the Writing one, but it doesn't matter. You'll see an integral button under typesetting. Definite integral right there. 0, 5, f of t dt. Remember, you use underscores when you first define functions. You don't use them after that point. This is going to be 125 over 3. Mathematica is using the fundamental theorem of calculus to find that. And yes, that is 41.6 repeating. Mathematica is rounding there. What about the Riemann sum thing? Well, it's a little tricky. Let's see if Mathematica will evaluate this sum. I just pressed the summation button right there, right next to the integral. I goes from 1 to n. F of xi times delta x. Well, how do I type that in? Well, remember, xi is a plus I times delta x, and delta x is b minus a over n. Where for our problem, a is 0 and b is 5. Time 0 to time 5. So delta x would be 5 minus 0 over n, 5 over n. And I guess this would be 0 plus I times 5 over n, which is just 5i over n. Got that? A is 0, B is 5. Delta x is going to be 5 minus 0 over n is 5 over n. And xi, which is a plus I times delta x, is going to be 0 plus I times 5 over n is 5i over n. I guess that's what I'd have to type into here. Xi is 5i over n, and delta x is 5 over n. Can Mathematica evaluate the summation even though it doesn't know what n is? Let's see. Yeah. How about that? It's for the function t squared. If I used a different function, I'd get a different answer. Isn't that weird? It worked. Is that difficult to prove? It's tricky. You can use something called induction to prove it, though where the formula comes from in the first place is a bit of a mystery. It is related to the fact that we've got formulas for the sum of the first n numbers. It's related to the fact that this summation is n times n plus 1 over 2. And also related to the fact that this summation is n times n plus 1 times 2n plus 1 over 6. Actually, if you're really interested in knowing why, I made a video about it on my YouTube channel like a month ago for a different class called numerical analysis. You can look on my page and you'll see a thumbnail where I talk about this if you're really interested in where these formulas come from. Anyway, what are we going to do with this? We're going to take a limit of this as n goes to infinity. Mathematica. What happened? It's stolen. Mathematica, what's limit of this as n goes to infinity? 125 over 3. Same answer. Like magic. Poof. Same answer. Is it magic? No, it's rigorous math. It only feels like magic. It's hard, rigorous math. That's why it feels like magic. Actually, you wouldn't even have to put this in Mathematica. You could figure it out on your own if you got this formula, because it's a rational function of n, where the degree of the top and the bottom are the same. I could expand it perhaps here, or simplify it. Well, no, let's try simplify. Simplify. Well, okay, it's not really working. I could expand the top. Let's expand the top. It's a rational function. Expand. It's a rational function of n where the top is 125 plus 375n plus 250 over n squared, and the bottom is 6n squared. As n goes to infinity, you know back from chapter 1 that the limit of that is going to be the ratio of the coefficients to the highest powers, when the degree of the top and the bottom are the same. 125 over, or 250 over 6 is 125 over 3. I mean, the main mystery is, where does this come from? That's the main mystery here. And why? Well, the other mystery is, why did it give us the same answer? I hope it makes intuitive sense, though, because you are finding the area under the curve. You're approximating it first with finitely many areas of finitely many rectangles, but you're letting the number of rectangles go to infinity. They're getting skinnier and skinnier. Delta x is going to 0. Could I also do it with the delta x? I could also write this as the limit as delta x goes to 0 of the same kind of summation. Could I also get Mathematica to do that? I think so. I haven't tried it that way, actually, to tell you the truth. Let's see, what would I need to change here? I'd write an I times delta x in here, I guess. And I just write a delta x over here. Although then the n's not in there. I guess it is kind of a problem, right, doing it that way. Yeah. You got to get it in terms of n if you're going to write it this way. I guess that doesn't work. But I can still write it this way by hand. That's still fine. I just can't put it in the computer. All these rectangles have the same width, delta x. Letting the number of rectangles go to infinity is the same as letting the width of all the rectangles go to 0. Again, I did a right-hand Riemann sum. I could have done a left-hand Riemann sum. Technically, the summation would have been different. If I do this summation and let I go from 0 to n minus 1 instead of 1 to n, I do get a different answer here for the summation. This, take note of it, is different than this. There's no minus signs in that expression. There are minus signs down here. But the limit is still the same. Still 125 over 3. To end class today, we should emphasize something else. What if the bug moves back and forth? What if it really is a velocity that's sometimes positive and sometimes negative? V equals f of t equals, let's say, how about 2 minus t over the interval from 0 to 5. So now the velocity is starting out positive at 2, but by the time you get to time 5, it's down to -3. Slope of -1 here. You could ask two questions. So the bug is traveling back and forth, first to the right, then the left. You could ask two questions. How far did the bug travel? And what's the change in the bug's position? And the answers to those questions are different. The integral of the velocity, it is a true velocity here, not speed, sometimes positive, sometimes negative, is the change in position, not the distance traveled. The integral of this from 0 to 5 of 2 minus t is now the change in position. Change in position, which with back and forth motion is not the same as distance travel. Distance travel is literally how far did the bug walk? First this way, then back this way. Change in position is what is the change in position along a number line from the starting point to the ending point. And in fact, because the bug walks with a velocity that's more often negative than positive, you might say, the bug ends up to the left of where it started, its change in position is going to be negative. This integral is going to be negative. If you use the fundamental theorem of calculus, FTC, find an antiderivative of 2 minus t, you get 2t minus 1/2 t squared. Check it in your mind. The derivative of that is 2 minus t. Evaluate from 0 to 5. So we plug in 5, 2 times 5 minus 1/2 times 5 squared, and then subtract what you get when you plug in 0. It is convenient to use 0 for the lower limit because then lots of times you get zeros. Doesn't have to happen. Gives 10 minus 25 halves minus 0 minus 0. And that's a big 0. 10 is 20 over 2. 20 over 2 minus 25 over 2 is negative 5 over 2. Negative 2.5 centimeters is not the distance traveled, it's the change in position. Can it be interpreted as an area? Not in the usual kind of way, but it is related to areas. It's the area under the curve when the curve is above the axis, minus the area above the curve when the curve is below the axis. This area, let's see, when is it going to cross the axis? Is the 2. That area is 1/2 times base times height is 2. That's the area. This area is 1/2 times base times height is 9/2 or 4.5. Yes, 2 minus 4.5 is negative 2.5, and that matches the answer. It's the area under the curve when the curve is above the axis minus the area above the curve when the curve is below the axis. Sometimes called a signed area. Quote unquote under the curve, though it's not always under. A signed area between the curve and the horizontal axis. That's what the integral represents. And it gives you the change in position. That's what you want it to represent. That's the best thing to let it represent here. So what's the distance traveled? The distance traveled would be the integral of the speed still, but the speed is now the absolute value of the velocity. Absolute value of 2 minus t. Let's just do that geometrically. If I take the absolute value of the speed, I get a graph that looks like this. And the distance traveled is the area under this curve, because this curve is always above the axis. Add up the areas of these two triangles. This area is still 2. This area is still 4.5. The distance traveled is 2 plus 4.5 is 6.5 centimeters. What's happening here is the bug goes to the right 2 centimeters before going to the left 4.5 centimeters and ends. So it goes to the right 2 centimeters, then goes to the left by 4.5 centimeters. and ends at negative 2.5 centimeters for its location along the number line there. I didn't draw that perfectly. That's the idea of what's going on. First to the right, then to the left. You had some homework problems that also involve dealing with tables of data. The tables of data problems, you're really just doing these summations. That's all you're doing. You don't even necessarily have a graph. You got the function values, you got your delta X or your delta T. You can do these things. You can also average these two. Average the values of the left and right hand sums. Add them up and divide by 2. It's called the trapezoid sum. Problem solving video, I think I do at least one example like that. Okay. Have a good weekend.